It's my pleasure to introduce Vinayak. He is an associate professor in the Department of Mechanical Engineering and an affiliated faculty in the Department of Computer Science at Texas A&M. He leads the Mixed Initiative Design Lab, and his work is around interface, is at the interface of geometric and topological computing, human-computer interaction, and AI, among other topics. And we connected a few months ago and was hoping to share, I was hoping that he would share some of his work because I found it very relevant, especially to the generative assembly design outcome. But his research is kind of in different domains like metamaterials, extended reality for design, computational fabrication, and collaborative design. So, yeah, thank you in join me in welcoming Vinayak, and I'll leave it to you.
Right. Thank you so much, Daniel and GU, and thanks, Daniel, for inviting me to this talk. So first of all, since I am sitting in Texas here, howdy to everybody. um, now, you know, I uh, I've been at A&M since 2016, and since the day I arrived at the US in 2011, that was my first day of PhD, there has been a copious amount of technological development, right? Particularly pertaining to design. And so what I wanted to do today was sort of put forth some of my perspectives from three different angles, if you will, right? uh, 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 thinking about design from the perceptual side, from the cognitive side, as well as from the action side. And so I thought that I'll share the research that I've been doing more as stories rather than just a bunch of numbers. Of course, a little bit of that will be there, but my goal today is to sort of try to think about this whole idea of design on the computer from a very human perspective. Okay. Now, as Danny introduced, I run the Mixed Initiative Design Lab, and a large part of my work has involved geometry in some or the other way, regardless of my stage of career. Starting from my undergrad, I've been thinking about and working with geometry. Uh, I've also, on the other side, been thinking about how humans interact with computers, and then in a more recent sense, I've been working a lot on how human and computational agents interact with each other, right? So you'll see that uh, regardless of whatever I do, all these three things sort of are trying to serve the bigger umbrella of design in some or the other way. And my hope is to see whether we can find some underlying connections across the three domains today. So this is just to show you the craziness of the kinds of things that we do in the lab. These are some of the projects that we have. So you'll see we have spatial user interfaces, we have data analytics and digital twin. We are also doing some work in shape abstraction for autonomous vehicles, applying machine learning to medical imaging. In fact, one of the most cited papers that I have, believe it or not, are in dentistry of all places, right? So I've been all across the board, and I've always kept that connection of geometry and of interactivity at some or the other level. Okay. Uh, Now, given this, right, let's dive directly into those three stories. And I want to start with the embodied story, right? It's a collaboration across multiple faculty at A&M, Dr. Quek, Dr. Sweda, and then we have three fabulous students who have been working. Two of them graduated, in the previous years. Let me give you some historical backdrop of this, okay? So this is me at 5:23 a.m. on 23rd of January 2012. Okay. I used to be nice, lean, and slim. At 26, you can do anything. You can eat a hoagie once a day at 2 a.m. and expect nothing to happen to your body, right? But in those days, the other thing that was happening was the Kinect, right? The Kinect had just come, I think, in 2010, and people were going gaga about it. So my advisor said, hey, I want you, this is your PhD story, right? I want you to be able to move your hands and create a shape. I said, fine, right? So as a first year PhD student, I found the simplest possible thing I could do, right? I knew sweeps, okay? And I just started generating some stuff using skeletal models, only to realize way late in my career that, when you think about this from the perspective of design and not as a computer scientist, there are so many other very critical things that need to be integrated for this to make any sense for design. Okay, if you think about how we interact with the physical world, right? We know that from an early age we develop hand-eye coordination, right? And as we go through the ages, we develop a lot of fine motoric perception. Okay, we develop a lot of precise motor control. Okay, and all of these aspects of our interaction with the physical world, you'll notice, happen here in front of my eyes, right? They happen in this peripersonal space. So now, with this perspective, you look at the video that I showed you, right? In order for somebody to truly come and design something, not just create a shape, there has to be a whole lot of work that needs to be done. Okay, so as opposed to that, if you were to look at the development in the AR, VR, and mixed reality side, right, right from the early times, right, one of the issues that has been there is that you can apply a lot of embodied interactions and spatial interfaces for video games and those kinds of things where the interaction is happening at a distance. But when it comes to wrist and finger level control, that is the stuff that is useful to design, there's still a lot of knowledge gap. So this was some of my motivation for my early work, going all the way through the first few years of my stay here at A&M as well. Okay, so I'm going to show one example of one of the works that we have been doing for the last 3 to 4 years. Okay, we were looking at this idea of prototyping for ideation. Okay, one of the reasons why prototyping is great for ideation is that you're working with tangible things. It allows you to think and ask better questions about the artifact that you're trying to design, right? So you're sort of trying to think by building. And there's been a lot of work in design theory literature where people have explored this idea of quick and dirty prototyping, both with and without the use of computational aids, right? So people have looked into this notion of prototyping for ideation. But once again, when you think about it in the context of spatial interfaces, again, a lot of work, right? If you look at some of even my earlier work, most of this work would identify with freehand spatial interactions at an arm's length, right? And this you will see also in the context of different types of prototyping for interactions. So there's this very nice work by Yue in 2017 that does this nice wireframe prototyping, those kinds of things, right? And this is some of my own earlier work where we were trying to integrate touch, that is some sense of tangibility to spatial interactions. So people have been looking at this notion of integrating tangibility with spatial interactions so that you can do more precise action, which means that you need to learn less about how to run the interface or how to work in the interface and focus on the design task, right? So the basic gap that we found was understanding of tangible interactions is still, I shouldn't say nascent, but it still requires a lot of work to be actually used for virtual prototyping. Okay, so in order to sort of explore this situation, this particular story on embodied interactions explores this notion of wireframe modeling, right? And I've already shown you that there are quite a few works that talk about wireframing for 3D product design. Okay, so this is the idea. The idea is called tangible stimulus. Okay, uh, imagine that you have a mixed reality environment. In the current state of affairs, the mixing in the mixed reality environment happens at the visual level. That is, there is a physical environment. I'm looking at that physical environment through glasses or camera or something like that, right? And then there are virtual objects overlain, and then I'm looking at the virtual objects in the context of the physical space. Great. What we are trying to, or we were trying to ask in this work was, well, can you do the same thing with haptics or tangibility, right? So this is one example of such an exploration that we were trying to do, right? So imagine that in addition to a visual counterpart, or rather instead of a visual counterpart, imagine that you had a tangible counterpart, right? So in this case, the head, the digital head and the physical head are mapped together. I am drawing directly on the physical head, right? And I'm drawing a digital object. One of the cool things that I can do here is I can still utilize the digital haptics beyond the tangibility of the head in order to explore space around the head. So this is kind of one idea that we had been playing around with, and we did a preliminary user study on it. So these are some key findings of that, right? The goal of my experiment was to figure out what role this kind of tangible stimulation could play in supporting design ideation. So I'm talking about early stage idea generation. I'm not talking about detailed design, right? I want quick and dirty, okay? So what we did was that, suppose I give to you an interface without the physical object, which is kind of what we do in a regular haptics interface, right? So you still have the haptic feedback, but you don't have the physical head over there. You don't have the tangible context over there, right? What would be the differences, right? Which tangible stimulus would reduce barrier to entry? Which kind of stimulus would offer potential for improved ideation? Does this reduced barrier to entry correlate with any improvement in ideation, right? And why and how, and so on and so forth. So these were some of the questions that we were trying to investigate. So what we did was that, okay, let's have two groups, right? Physical group, you have the head, and the virtual group, you don't have the head or the physical model, right? Now, of course, from a basic interaction point of view, obviously you can think about this as well. Can I do target reaching properly? Can I do basic curve tracing properly, and so on and so forth, right? But then, from a design point of view, you can also explore how do people think about ideas in each of these types of modalities, right? So we created this superhero themed design task where people were asked to create helmets and shoes, okay, for kids while riding a bike. Okay, and because these are for kids, the idea was to see if our design participants could create superhero themed helmets. So there is a visual and aesthetic aspect to it also. Okay, these are some of the shapes that that our participants generated, and you can see there are some clear distinctions between at least in a visual sense, between the kinds of things that people were generating on the physical object versus on the virtual object. You'll see some higher level of detail in the virtual group, but then you will also see some other types of characteristics in the physical group. So I'm going to very briefly touch upon what kinds of differences we saw, at least numerically. Okay, so in terms of measurement, uh, one question we had was, what tangible stimulus is better to reduce barrier to entry? Okay, one of the ways to measure it is to say that, well, how much energy does the participant spend? And you can actually calculate that using some basic parameters for each of the hand. Okay, and mind you that this is a bimanual operation, right? So for each hand, it's a completely different type of energy spent, and for completely different types of activities or atomic activities during the interaction, right? The other two questions essentially pertain to design ideation. So here there are some standard metrics that the design theory folks have invented maybe in the 90s or so, right? So you can think about novelty of ideas, variety of ideas, quality. Now quality can be a little tricky, right? So for example, quality is contextual. So in this case, if I'm trying to design a helmet, I would say, well, safety would be important, comfort would be important, fit would be important, and because I have a visual cue, superhero, aesthetics would also be important. Okay, so for the ideation metrics, we basically do a typical inter-rater reliability study. We call 2 or 3 design experts. They are individually coding the process, as well as they're evaluating each of the concepts, design concepts by each of the participants, and then they are coming to some kind of a consensus. Okay. So let's look at some interesting results, right? So let's look at the energy spent. If you look at the energy spent by each hand across both the interface, so the stylus and the turntable, right? The stylus is the hand that is holding the pen. The turntable is the hand that is rotating the object. Okay. You can obviously see that a significantly lower amount of energy is spent in turntable, which is kind of expected. No problem. Now let's consider the energy spent by each hand. Okay. And here, one of the things that we did was, remember that the person who is turning the table with the physical head, they are spending more energy generally because the head has weight, right? The turntable without the head does not have the weight of the head. Okay, so if we consider the weights of the head, then what do we see? So you will see that in case of the dominant hand, that is the hand that is holding the pen, you have essentially no significant difference, right? For the non-dominant hand, we can't say. Okay. If we don't consider the model weights, then energy spent by each hand looks something like this. Okay. And here again, you'll see that dominant hand, you have a slightly lower p-value, but for the non-dominant hand, you have a relatively high p-value. Okay. But what does this mean from the perspective of ideation? Is there any way for us to reason about what those people did because of which we are seeing this measurement? Okay, so let's look at the ideation metrics. In terms of novelty, you'll see that the physical group was generally deemed as the group with higher novelty. Okay, but when you look at variety, you will see variety is roughly the same across the two groups. The most interesting bit comes in quality. And this is a very, very important aspect that connects to the notion of adding physicality to spatial interactions. So in quality, you will see that the raters rated the virtual group better. Does anybody have a guess why? So people in, the raters are saying that the quality, basically the fit, the comfort, or the perceived fit, the perceived comfort, the perceived safety are better in the virtual scenario where there is only haptics, like no physical object. Anybody has a guess? I hope I can elicit some responses from people in the chat box. Better fit. Okay. Physical constraints add accuracy to the strokes. Okay. All right. Now, so actually, both Daniel and Fraser are in the right direction. You see, what happens is, without the physical object, folks were really, really bent on making the thing accurately fit on the head, right? On the physical object, they always wanted to be slightly away from the physical head model. Okay. Now that was perceived by the raters as bad fit. Okay. What the users were trying to do was to say that, well, the helmet has to have some tolerance. I'm going to put it slightly away in the physical case because the physical object is there. In the virtual case, the digital haptic feedback essentially was the only thing for them to figure out where I need to draw the curve. Okay, which was then interpreted by our raters as, oh, this is better fit, or it is more safe, that kind of stuff, right? So a simple change of modality, well, of course, it's not simple, but a unit change of modality between tangibility and lack thereof completely changes the way that people interact with the same type of system for the same type of task. Okay. So, broadly speaking, and remember that I'm not showing you all the project in all its glory, but the point of the story is to think about the following, right? Where the action is. We are thinking about embodied interactions, right? different type of stimuli, they will change the design outcome. We saw that, right? In terms of both novelty, variety, novelty at least, and in terms of the quality, right? Why? Because they encourage different types of processes due to different behavior of the user, right? The key learning that has happened, at least in my case, personal learning from that video that I showed you, creating like a huge pot, is that there has to, in the context of spatial interactions, there has to be a balance between user performance and user experience, right? Uh, Particularly when we are talking about things like idea generation. In idea generation, the question that we need to ask is, how real is real enough? Okay, because a lot of times, like particularly in the domains of spatial and tangible interactions and AR and VR, at least from a visual point of view, people have spent a lot of time, money, effort, and manpower in um, making things look realistic. Wonderful, right? But we also need to take into account this point that human beings also fill the gaps, right? So we want to be able to strike that balance, okay, where we decide what we want to value more, okay, the experience or performance, right? Going back to Michael Polanyi's statement, right? The body is the ultimate instrument of all our external knowledge. So I think that unless we also figure out how to make correct use of the body and of our embodiment within these environments, things like design in these kinds of environments are going to be difficult. But I think that that's a good problem to have. It's a problem which encourages more research into this area. So the broader perspective of this is what we have called clockmaker's workspace, right? Thinking about bimanual, proprioceptive, and multimodal spaces. So not just visual mixing, but also haptic mixing, right? Different types of view manipulation. And this is, again, not an uncharted area. Many people have worked on adaptive views, but the effects of all these things combined onto design is still something difficult or challenging, because design is at the cognitive level. It is, so we are talking about the connectivity between the perception, action, and cognition cycle, right? But at the same time, at least I would like to say that for things like design in virtual environments, close to body interactions are important, because that's where we hold we hold things personal. That's where we make things precise, and this may indicate a market pull for some eventual technology on the haptics and kinesthetic side. There is a I am really happy to say that I've seen a lot of papers in Chi-West and all that, and IEEE VR or transactions on haptics, on new haptics technology. But I think that that's a very rich area that we need to discover more. And I think physics is a barrier over there, right? So I'll end this story with Gibson's quote. I really love this quote, right? He says, "We must perceive in order to move, but we must also move in order to perceive," right? And so while we've been looking at the perception side of things on the technology front, we must probably look at the movement or the action side of things and integrate them together. So this is sort of my first story in terms of the kinds of things that I've been exploring from the perspective of design. The second story is what I call the generative story, and the flavor is going to change very significantly here. And this is an ongoing, very, very large scale project. When I say large scale, I mean there are collaborators across the world on this project, right? We have people from Glasgow, we have people from Monash in Australia, we have people from where else? We have people from India, and a couple of places, other places in Europe. And this primarily focuses on the geometric and topological computing aspects of my work. Okay, this is how this all started, right? One of the key things that I learned during my PhD was that we are, again, in the context of computational design or designing with a computer or using a computer, we are still along the track or walking along the track towards this idea where people are not just recording or producing shapes, right? They are actually thinking through the tool. A beautiful example of this is one of the teams, project teams in my product design class at graduate level. So there's four guys, okay, who are in a team, and they were designing some, physical artifact like a staircase or something like that. These guys, despite my repeated lecturing about hand sketching, they actually chose to use SolidWorks as a means to do idea generation. And I mean idea generation, like 50, 100. So sometimes, people, when a tool becomes second nature to you, you tend to use it in creative ways. And I think that that's where the creativity aspect needs to be studied in design, not just in the outcome, but in the process. How is a person using a tool? Okay. But coming back to this, right? In the context of complex 3D objects, which is now very common when you look at in topology or Autodesk generative design or any other generative design tool, one of the things that has always bugged me is how do we get a person to make sense of what is happening, what would happen if my shape is like that. Thinking about it from a product design perspective is one thing, but then looking at complex geometries, it's a whole different model of working altogether. So since I'm talking at Autodesk, I think this is something that everybody would understand, right? So uh, by and large, the philosophy of designing shapes has been to say that, well, uh, I can represent a shape as a hierarchical a composition of simpler things. And the way I compose is based on a bottom-up design. So therefore, we get a tree-like structure. This is nothing new to, I believe, any of us were sitting in this talk today. And we achieve this composition through Boolean operations as they are defined in set theory. Okay. And by and large, most mechanical CAD tools, whichever one we take, are kind of based on some combination of this principle and parametric geometry. And I'm not talking about uh, computer implementation here. I'm talking about this from a philosophical or a representational point of view. So this is cool because this is great for forward design, right? I want to make a mug, so I will create a vessel, I will subtract some volume, I'll create some torus, cut it in half, put it as a handle. So great for forward design, right? Because it allows me to express my design intent. Great. So it has worked fairly well for general product design. Now, I have been thinking about, well, what you can do in similar fashion for generative design or design where we're talking about patterned materials or complex geometries and things like that, beyond just putting in parameters that create some kind of an implicit model, that create some kind of a level set, and so on and so forth, right? So we've been toying with this idea of partitive geometry. This is a paradigmatic idea. The notion is to say that instead of thinking about a shape as a composition of simpler shapes, I am going to think about a shape as a decomposition of a volumetric domain. Okay, so represent a shape as a partition of some monolith, right? So in some sense, I am thinking about it more in a top-down manner rather than a bottom-up manner. Okay, so I'm not interested in the individual shape. I am interested in how interestingly can I break a given piece of volume in space. Okay, and so the representation of a partitive model is a skeletal representation. So I basically have a bunch of skeleta that are arranged in space according to some set of rules. We'll get into that a little more. And my original purpose was to bring interactivity to generative design so that we could intentionally design complex geometry. And when I say intentionally, actually, I mean to say that a person should be able to sketch this skeleton out and say, bang, now pattern it. Now, this is the shape that I get, and I should be able to tell what final shape I'm going to get. Of course, there's a whole lot of work to bridge that gap between forward and inverse design. So I don't know how to achieve this purpose yet because we have been primarily working or exploring the representational idea thus far, right? But the hope is that one day we might be able to get here. So this is the story behind this notion of partitive geometry. Uh, How many of you are fans of any one of these channels? Is there any fan of number file, 3 blue, 1 brown? That's actually my personal favorite. I use it sometimes in my classroom also. Anybody here? If not, yeah, excellent. Thank you, Levi. Great. So, I have this tendency to keep watching random videos from one of these channels. And in the year 2018, I was watching this video by Matt, who was the stand-up math guy. Okay, and he's saying, "What is a scutoid?" I said, "Okay, it looks like an interesting shape. Let's watch the video." Essentially, scutoid was this very nice, weird shape that was quote unquote discovered by a bunch of people who were studying animal skin cells, epithelial cells. Okay. So this is what they were trying to say in the paper. It's a Nature paper, very, very nice paper. You should definitely read it if you get your hands on it. So they said that, well, when you look at skin as a bunch of cells, typically this is what people will visualize those cells, right? So you have some kind of a prism, okay, which is sort of connected to other prisms in a space filling or a watertight fashion, right? The problem is when you bend the skin, right, then what happens to these prisms? So the common visualization that people or imagination people had was, well, the prism becomes a frustum. What's the big deal? The problem is this: the skin is highly, highly deformable. Okay, if you look at our intestine or even just the general skin of the body, it is very, very deformable. So how small of a of an apex of the frustum do you want to create, right? Is it just going to converge to a point? That's probably not how natural shape would occur. So this team of people led by Gomez Galvez, and they said, you know what? There are many different possibilities here, right? You could have a prism, you could have a frustum, you could even have a prismatoid. Why? Because the apical, that is the top layer, and the basal layer, that is the bottom layer, for one given cell may actually be two completely different shapes, meaning you could have a pentagon below and a hexagon above. Then what do you do? There is a topological difference, no? So how do you figure that topological difference out? So they said it's none of these. It's this thing called the scutoid, okay, which is what I'm showing you to the rightmost corner. When I looked at it, I said, well, this is the unique feature of this particular shape, right? And as a computational design person, my first question is, can I will this to happen? That is, I would like to create some kind of a nice structure where this V shape is something that I can control. Wherever I want, it should be there. What's the rule? What's the law that governs this? So when I had this question, I emailed my good friend, Professor Ackelman. And over the next 3-4 emails, we basically figured out the algorithm, only to realize later that the paper had the algorithm in the supplemental material. Whenever you think you have original ideas, you actually have egg on your face, right? So I'm sort of thinking about this whole point idea, and we want to look at where this bifurcation is happening. So if you look at this, shape, the scutoid shape, one thing to note is that it always comes in pairs, at least in pairs. Okay, that's an important observation. Second is, if you now imagine that you are slicing this pair, okay, layer by layer, just like a 3D printer, but in the opposite direction, okay, there's this nice topological shift that is happening, right? If you look at this magnified view right here, okay, one edge is combining into a point, and then it's collapsing to a point, and then it is expanding back into an edge in a different direction, which is kind of what you see right here in these V shapes, right? This is the edge collapsing, and this is the edge expanding in the other direction. Okay, so what can we say about this property from a geometric perspective, right? That was the question that I was trying to answer. Okay, you'll see that because we are talking about cells, skin cells, one of the important things is they have to retain fluid, which means that they should be packed in a watertight manner. In fact, the word watertight itself, signifies that, right? It is watertight, so no water passes through, which means that there should be no gaps between any two adjacent cells. Okay, so that's one point, which is why they are coming in pairs. But then they are also showing this nice bifurcation property, and both these are connected by a common principle, which is, by the way, a very well-known principle for a very long time, both to geometers as well as to scientists from various fields in natural philosophy, right? The idea is that of tessellations, right? Particularly Voronoi tessellations or Dirichlet tessellations, right? So if you look at patterns in nature, many patterns share a common element. The common element is that of growth, right? So if you look at this particular animation on the right hand side, basically these are all bubbles that are emanating from a point, and wherever they interface with another growing bubble, they stop, right? So nature is basically saying, I have a couple of simple rules. Everything is going to grow, but it's not going to intersect itself, and it's not going to intersect anything else. Like whenever it meets something else, it stops. This is the fundamental property that guides both the aspects, the space filling, the water tightness aspect, as well as the topological shift aspect. And I'll show you how, okay, through the three principles of partitive geometry. So the first principle is that because I want to decompose a volume in a partitive sense, I want to partition a volume, I want to have some kind of space filling or water tightness property. In literature, if you look at the things that geometers have said, they said, well, and mathematicians, they like to catalog and categorize and count things, right? How many of these shapes will there? They said, well, if you think about convex polyhedra, there are only 8 space filling convex polyhedra. Space filling meaning two things. One is that there is water tightness. Two is that each one of them is identical, meaning that, I have one hexagonal prism. I can repeat that entire hexagonal prism in space ad infinitum, and I will fill the space. So that is space filling. They said that there are only 8 space filling convex polyhedra, and then only 5 of them have regular faces. This seems very, very discouraging because, partition can happen only in these following ways, right? But when you notice, at least the watertight property is abundant in nature, which is what Voronoi's principle was. Voronoi was originally a crystallographer. He was looking at crystal symmetries and those kinds of things, which is why we also call symmetric groups as crystallographic groups. So there must be something more to it. And Voronoi gave a beautiful conjecture, okay, which I don't know why, but it got lost in the crowd of so many other papers that have used Voronoi's tessellation, both in computational geometry and outside, right? So let's look at a simple Voronoi tessellation, right? Well, the basic idea is that given a point, suppose I take this cell, this green cell, light green cell, any point on this cell is closest to its generating site, right? Any edge that connects this to any other is the locus of points that is equidistant from the two generating sites, and so on and so forth. Okay. Now, let us make these black dots move. Okay. So when these black dot moves, look at what is happening. You see the topology of the cells changes. Now you can observe that there are some edges that contract and some edges that expand from a point, and so on and so forth. Okay. Instead of looking at this as an animation, let's look at it as if we were 3D printing this animation in a stack. Okay. So this is layer 0. Those are my set of points. Imagine that I apply a trajectory to each of these points. Okay. When I apply this trajectory, and let's say I look at only this particular one, let's see what kind of shape will emerge. So you'll see that nice bifurcation is emerging. Of course, it's random, so it doesn't really look good. Well, that's besides the point. Aesthetics is in the eye of the beholder. But my question was, how do I control this? I want that bifurcation, that topological shift to happen at will, okay? Which is where the second principle of partitive geometry comes into play, which is symmetries, okay? So we want to be able to design complex structures, right, that are repeatable and that fill the entire space. Why fill the entire space? As I said, because I want to partition a given domain. And I need them to be understandable, because symmetries would then help me understand how to design, how to control the behavior and the ensuing properties of the systems that we could design using these kinds of things. So we use a beautiful principle according to Voronoi, he says that, boss, if you arrange those points in some nice fashion, you're actually going to get identical shapes. Okay, this is the Voronoi conjecture, and it applies to arbitrary d-dimensional space. Okay, so I have this random set of points and I have this trajectory. I look at some symmetry. So these are two-dimensional symmetries. So what I want to do is I want to apply symmetry at every layer. Okay, and then I want to collate them and I want to see whether I get a nice shape or not. Okay, so you see, this is one example. This is, I'm showing you an arbitrary example where you'll see the bottom one is basically your P6 symmetry. Okay, rather actually it's P6M. Okay, now when I apply this across the board, this is what I end up getting. Right, so I am arranging my points according to some symmetry. The resulting shape that I get has that nice V thingy, but it is also space filling. That is, I can take the exact same shape and I can fill the entire space, just like I could do with a cube. Okay, so this gives us some encouragement as to, we have a design space finally to partition solids. Okay. Here comes the third principle of partitive geometry, which is higher dimensional sites. And once again, this, even though there have been hints in literature, people have not really capitalized on this particular aspect. So the question is, do we really need to go layer by layer, right? Imagine that instead of points in every layer, I considered lines in total. Okay, and I arranged those lines in space. Now, of course, a point is expanding into a circular bubble. A line would expand into a capsular bubble, right? But the principle of Voronoi remains the same. You will see that you get the exact same shape, which means that thinking about Voronoi sites beyond points actually gives you a huge design space to work with. Okay. So the third principle of higher dimensional sites essentially brings us to this final collated state of partitive geometry, where we are saying that in order to partition, we need Voronoi. In order to control that partition, we need symmetry, right? And in order to explore and investigate design spaces, we need higher dimensional sites. Okay. Before I move forward, a quick geometry quiz. I really like doing this. Can somebody tell me what this curve is that I'm showing you right here? What is this curve? Can anybody guess?
It's a fair question. Into a point? Or?
So if okay, let me see if I can add it. So let me change my color. So okay, there you go. This guy, right? All of these curves are identical, by the way. This curve, the same curve. Okay, the same, exact same, right? But what is this curve? It's obviously not a straight line. Is it a circle?
Parabola, I guess.
Yes, that's exactly right. It's parabola, right? This is your directrix, and this is your focus point, right? So this guy right here. Okay, so that's great. Now, so we kind of started realizing that because of the way in which we were constructing these shapes, we both in 2D and 3D were actually going to end up getting analytic curves and surfaces, which is great because if I wanted a nice computational representation, I actually have that, right? I have a skeletal representation, but I can also get a nice analytic representation, which could reduce computational complexity for representation, rendering, and those kinds of things in a more design context. Okay, so at the end, these three principles allow you to do a lot of things. So, for example, you can choose what you want to partition, right? That is the shape of the domain. You can also choose what type of arrangement you can use. This is the big one. You can choose any type of Voronoi site. I mean, this is completely up to you. This is where the designer's intuition and creativity may come into picture. And lastly, which is something that we haven't yet explored, but is a huge problem space for us, is when we apply Voronoi, we assume L2 norm, but we can use other norms and it will completely change the shape for the same set of sites and the same set of spatial arrangements. Okay. So with this, we have been doing a whole lot of applications. This is the first one, and I'll go through this a little quickly because we are at the 10:48 mark. Okay, so we explored auxetic structures using woven symmetries. We also explored the same auxetic structures, but for multifunctional, multi-scale materials. We have also been exploring, and this is an ongoing project, which we explored called cooperative 3D printing, where we specifically used this layer-wise idea to simplify the kinematics for the robots to cooperate without collision on a layer by layer basis. So this is layer wise cooperation, but then the end shape that you get is actually interlocked, which increases certain nice properties for the final print that you get. Okay. And so we have been developing all these different types of interlock tessellations, particularly for cooperative 3D printing, for layer-wise cooperation. This is a big project that is in collaboration with Zhengwei Shah at UT Austin, and then Wenchao Zhao in the University of Arkansas. And we've been working very closely with them. This is one of our more recent prints that we got from a 3 printer system. I mean, as such, computationally, you can go to any number of printers, but there are physical constraints, obviously. Okay. We have also been working on impact-resistant materials and volumetric metamaterials. By the way, just a quick note, because before I move on from this, is this is for the first time, at least to my knowledge, that we can systematically generate arbitrary genus tiles that uniformly fill the entire space. It's not that people would not have recognized unique cases before, but a systematic way of generating these has not yet been there. So, we're sort of very proud of this achievement, and we are working a lot on exploring how to think about architected materials design using this. So the big picture for partitive geometry, again, as I said, to me, linking to ideation is very important. When we think about generative design right now, some of the steps that have been taken in commercial tools is great in the sense that people want to make designers think more about the design problem and so on and so forth. But then it also makes the input geometry part of it black box, right? Because a large part of it involves some kind of intelligent systems, some kind of optimization algorithms, and so on and so forth. I am interested in understanding how we can make that whole process interactive so that I, as a designer, can take both atomic steps to change the shape as well as black box steps where I don't really want to care about the shape at the unit level, but more at a systems level, right? And for that, we need some simple and intuitive control. With that, I'm going to move on to my last story. And apologies for taking this much time. I hope some of it was interesting to folks at your end. But this is a project being done by Shantanu Vyas. He's actually here in the presentation today. One of my other students, Surya, and my earlier student, Tingju. And the story started because of my fanhood for Star Trek. Okay, so let's see. Okay, so there's going to be an end.
Now, form is it?
There you go.
Increase the table surface area by 20% and incline the top 15 degrees. Smoother, more metallic.
Computer, make this a metal table.
That's starting to look right.
Is there anything else in the room? Furniture? Chairs? Door? Other people? No. It was dark.
Yes, it was dark. Couldn't see beyond the table.
All right. I can watch this, for the rest of the day. But this Star Trek was something that I discovered during my PhD, and as I came in to Texas A&M, this is a true story, right? First day I meet Tingju, I said, I would like for people to be able to talk and the computer to be able to generate shape. Little did I know that it would take me on a very, very difficult journey in 2016, where we didn't have the tools that we currently have in the context of human AI collaboration, right? So we started, this is all pre-ChatGPT era, right? We started thinking about a simpler problem, saying, okay, can we at least think about textual stimuli to help people reflect? So one of the contexts that we were working on was mind mapping. Okay, and we wanted to see if I could create a nice game where a human and a computer are adding nodes of information, one after the other, and each of them are affecting the other. Right? This was a very, very early exploration, and at that time, the biggest data set that we had for this was ConceptNet. Okay. And we got a lot of flack from the design community because people wanted more technical data and so on and so forth. But over a period of time, we started thinking a little more about this idea of verbalization of shapes, right? So going to the broader context of design iteration, right? If I am in an iterative cycle, I am doing something, I'm designing, I'm implementing, meaning say sketching something out, and I'm evaluating. And there's been a whole lot of work from design theory perspective on this, right? So, Sean basically says, and I love this quote, right? Design process is a reflective cycle where the designer sees, moves, and sees. And this is very, very indicative of, I've this habit of watching a lot of art videos on YouTube. So you'll see that the artist will start with some random set of, strokes and curves, but there is an object that emerges out of the set of strokes. It's almost as if they're sculpting on paper, right? And so this notion of seeing, moving, and seeing essentially boils down to reflection in action and reflection on action, right? You can also look at design processes as a series of transformations, right? So I'm thinking about function, changing it to a structure, which is sort of giving me a behavior, and I'm taking that as an iterative cycle. So there's a whole lot of work, including some of my own work in the past, that has explored these kinds of iterative cycles in design. The main gap, at least from my perspective at that time, was a lot of this is very regimented, meaning that even if you're drawing a sketch, the representation, the geometric representation of the sketch, and then what you do with it later is very, very regimented. It's very difficult to collate all of that with something as free flowing as language. Okay, this has been a problem that I've had for a very long time. Okay, so what we wanted to do, instead of going the AI and ML way, which is to say that let's train a data set, we said no, let's do a study. Okay, that how do people actually verbalize during these design digital transformations? Okay, and can we then use that information, that insight, in order to think about how human AI collaboration would look like in a verbal or a conversational interface where reflection about what you're doing or the decisions you're taking becomes important. Okay, so what we did was we had this very nice program called Youth Adventure Program. And I used to do that almost on an annual basis, where a bunch of middle school and high school kids come, 13 to 17 year kids, and then we give them a design context, and then I teach them how to do CAD and how to do idea generation, so on and so forth. Okay, so that particular year, we said, let's do something related to Star Wars. That was our theme. Okay, so the goal was this: we created a very simple interface, and speech to text was kind of reasonable by that time. I think Shantanu will tell you this would be 2019 or 2020 or something like that. And then he said, okay, we are going to give you a standard template, right? It's a spaceship. You can do some simple things, right, to different parts. So I'm giving you a template. You can make changes, okay? And the changes are sort of pre-programmed, right? Because, we don't have the natural version of it yet. And we had these kids, these young students. They came and participated at the end of that entire design cycle. So we taught them ideation, prototyping, 3D modeling, and then on day 2 we did this user study. Okay, so we had roughly 10 participants. This was a more a qualitative study. And what we did was say, okay, do some practice, and then I give you an open-ended task. So just create as many different and wacky spaceships as you can. Okay, don't worry about good, bad, ugly. You think what you want to do, and you do it. You speak to the computer, say, and the computer will make the change. The key thing, was that we actually acted as a reflective partner in this study. So every time a participant would make a transformation, Shantanu would go and ask, why do you think you did this? What's the reason? What's the logic? We wanted to understand how people explicate functionality with form. We have come into this habit of splitting form, function, behavior, structure into neat little silos of silos in themselves. But I personally don't believe that that's what happens at the cognitive level. These things are sort of talking to each other time after time. So therefore you will never always find a person saying, I want to create a Bezier curve at 2 millimeter here. No, they'd say, let's make it round. Okay, that's one level of shape. But then they would say, I want it to be smoother because I want less stress over there, right? So there are different levels of communication that we have for the same design artifact, and that's what we wanted to understand. So this is a sample user task.
Playing shorter by 20%. Make the engines taller by 30%. Is that on the shape right now, or are you trying to find new sizes and see what kind of sizes fit best? So what is your plan with either changing shapes or sizes? I'm mostly trying to change the shape right now. Okay. To where it'll be a smaller sort of. Okay, overall smaller. Yeah.
Right. So this was one of the examples, and people have. I mean, these guys have such creative minds. They say things that we didn't expect. So these are some of the shapes that these participants were able to create. But the more important stuff comes in here, right? We could directly see that there are certain types of functional verbal cues that people give. So in terms of, say, capability or usability, or in terms of form, which is more preferential, that is changes made because of my personal preference, or experiential changes that I think would be useful because I have seen that stuff before, right? Or open-ended, I just want to figure out what's going on, right? So for example, add 4 wings, make wings shorter, right? And the reflection is I want it smaller because it's harder to hit a small thing, right? I'm sort of thinking about this metaphorically. This is the participant. These are the participants' words, right? It's harder to hit a small fly than a big, maybe 6-inch cockroach. So that's why I'm going for a more smaller set of wings or smaller body, because it's harder to hit. Or say human centricity, right? I think it will be best if some kind of an unmanned thing with a lot of power, because you can't really fit a person in there, probably lying down. Okay, experiential. I want to make a cool flat ship like a pancake, and so on. But then, as soon as we published this work, what happened? The best laid plans go to waste, right? Can somebody guess what happened? At the, this is something that is kind of obvious, right? This is all pre OpenAI or ChatGPT era, right? ChatGPT came. Okay. Thanks, Saran. Yeah. Okay. So ChatGPT came. So we then had to completely change our entire way of looking at it. So now this is the current work that we are doing. I'll be very brief about it and probably show you a video and end the talk there. But Shantanu has been working on this idea where instead of thinking about shapes and templates, suppose we wanted to talk about a more well-defined problem, right? Because we have realized that it's very hard to talk about general product design contexts from a verbal point of view. So he said, okay, let's take the standard optimization problem, right? Minimize mask, minimize deflection, okay? and apply this notion of reflective conversation to that, right? So a person can create structures, right? And then a person can ask questions. A person can also respond to some of the conversations that the agent is giving, right? So I'll show you a very quick video of this.
To help you explore,
Three around to see how that impacts the design objectives. That'll help me get a better idea of how to proceed further.
that sounds like a great approach. As you experiment with moving node 3, keep an eye on changes in the structure's balance and stability. Feel free to share any observations or questions you might have during the process.
So here the user is moving and watching what happens to the material percentage and the maximum deformation, right? So this is something where reflection is being implicitly happening.
I just moved node 3 around and realized my max deformation dropping quite a bit. Can you explain why that happened?
It seems moving node 3 helped create a clearer path for the load to travel from the bottom right to the left supports. Imagine bending a paperclip. If you hold it in a way that spreads out the force evenly, it bends less. Similarly, by repositioning node 3, you helped spread the forces more evenly through the structure, reducing bending and thus deformation. Does that make sense?
All right. So, oops, sorry. So this, this is sort of what we are trying to work with at this point of time, and the big question in my mind is, what should the agent know? Okay, you would have noticed that the conversation is happening at graph theory level. That is, move node 3, node 4. That's too specific. Is that something that is required? What's the level of knowledge or information that the agent must have about the design context, right? So we are looking at two different variations here. One is a context-rich agent that knows the process, which is what happened before, what is happening now, what is the the stress distribution, right? It also knows the design outcome. It knows that there is an optimal design and this is what it looks like. Not only that, it knows the design representation, right? It knows that there is a node to edge representation, not just an image. On the other side, suppose I had a more limited context agent where it knows the process, right, and the current state, but it does not know the final outcome. And we wanted to explore how conversations will change, how reflection will change, and what kinds of things will happen. What kinds of things would people make? Okay, so two simple experimental tasks, right? And we have just finished our 45 participant experiment, 15 participants per group. So we have no AI, limited context, and context rich, right? And these are two very basic tasks, right? An L bracket and and a simple cantilever type of a system. Okay. These are some preliminary findings. You see, so if you now look at the final shapes that people made, right, over the bunch of iterations, you'll see that the no agent guys, that is the guys who did not have any conversation, there's a huge number of nodes. Basically, they are very fast. They'll just keep on adding nodes, moving them, subtracting them, whatever, right? But they always ended up creating very, very high density, high complexity topologies. On the other side, you look at the context rich agent that knows everything, okay, which is talking in nodes. You'll see very, very simplistic models. And the limited context one lies somewhere in the middle. Below, I'm showing you a heat map visualization of the latent space of all the iterations that happened in a given group. And you can see the way the design space is dense at different regions in this space, right? So you'll see that you have a lot more high density regions in the context rich agent. This actually shows a lot more interestingly for the L bracket. Okay, so now here you can see the red zone is very, very limited in the context-rich agent, because interestingly, this happened to be a more simple problem for people to solve. So they got to the final answer rather quickly when you compare it with no agent or even limited agent. Okay, so once again, these are all preliminary findings. I won't go into the numerical stuff, but I'll just show you an example conversation, right? So say, with your recent adjustments, you reduce material usage, but deformation increased. What do you think could be the reason? So here we are trying to emulate agent initiated conversation where the agent is trying to make the person reflect by asking them questions. Q&A is a very well-known way of reflective thinking, right? So we are trying to now figure out how to model the conversation so that we can activate different types of reflective mechanisms in these types of tasks. Of course, my dream would be for a person to be able to design a more systemic level item like a table, but that's too complex, right? Even with this simple idea, the study of user and agent initiated interactions is very, very intriguing, right? Again, the design representation matters. Where I add, so the user, for the user to be able to ask, where should I add the node? The user and the computer both should know that this is represented as a node and edge, right? Now, in the limited access case, whenever this happens, the computer does not necessarily have an idea of the representation. So it responds in a more general fashion. You might argue that, well, people would be frustrated if I ask a specific question to the agent and it gives me a vague answer. You are right. They are frustrated. But I can also tell you that that frustration is sometimes required. Meaning that in the early stages of exploration, we found out that a more limited context model works really well in comparison to when you are at the later stages where the person is almost getting close to satisfying the objective function, which means that we need adaptive models for conversation for these types of tasks. Okay, so the big picture for this story is reflection on and reflection in action, right? We have seen a lot of times designers use analogies, and there's been a whole lot of work on design by analogy in design theory. How do we actually put that in to human AI collaborative contexts or conversational reflections, right? Second is, through this more recent work that we are doing, we also figured out that predictive information is actually very, very useful in making these conversations more meaningful. I'm only showing you the success cases. There have been a lot of failure cases also, by the way, because of the different ways in which prompting is done to the agent, right? And that's, I think, a very, very open question, but it will become a lot more complex when you complexify the design task itself, okay? So I'll end my talk with this slide. When Daniel was introducing, he said representation, perception, action, and cognition. In each of these three stories, I sort of explored one idea, but I think that there is a more deeper connection to this general set of components or aspects of design. One is representation. How do you represent the design artifact? Two, modality. How are you interacting with the artifact? And three, workflow. How is that interaction embodied within a sequence of things that may be iterative, that may be that may be creative, and so on and so forth, right? So I think that there is a whole lot of work that needs to be done in mapping that perception, action, cognition framework, which is coming from the human side, to the representation modality workflow framework, which is coming from the tool side. Okay, so with that, I'm going to thank all my collaborators and, of course, my students. They do all the work. I basically come and talk, and I would open the floor for questions. Thank you.
Great. Thank you so much. I know folks had to drop off.
Yeah, I'm so sorry. This took way long.
No
So
worries.
I'm hoping that this was reasonably interesting to
That's
folks.
very interesting. Very interesting. Do we have any questions from the remaining audience members? I actually had one. Oh, go ahead, Daniel.
No, I was gonna say if there are no questions, I have some notes and definitely I will follow up with you, Vinayak. Um, um,
Oh, there's a chat. I've heard. Okay, thank you.
Yeah, and folks are welcome to hop off. I know we did go over time. I actually had a question when you mentioned artists sculpting on paper. I thought that was a
Mm.
very interesting reference to your talk. Do you see your research also moving more into somatics? So similar to proprioception, but like a closer look into like embodied ideation or reflective making.
Absolutely. In fact, so you make a very interesting point here. See, what happens is, at least in academic research and in research in general, we try to separate a problem out so that we can study it in greater detail. But for at least for design and these types of things, I have somehow realized that perhaps having more modality is more useful. So from that point of view, I envision a scenario where some of the haptic stuff that I did is basically integrated with the conversational stuff that I'm doing. So imagine that I am actually creating a curve sculpting, and there is a conversational model that is talking about, it would be nice if this was soft. Oh, this is soft. So the material becomes soft. You understand? There is a whole lot of materiality to explore in the domain of conversationalism also, right? But then the question becomes, well, what are you really testing? Are you testing the perceptual side of things, how well a person can do? Or are you testing the cognitive side, which is in terms of their design process and the design outcome? It's a huge a huge space, right? But that's a very very nice question, Gio. But did I answer the question that you were talking about?
Yeah. I just thought it was interesting that you looped that in, like your observation about the sculpting part, because that was what I was thinking about when you showed the head interface and the drawing. So yeah, thank you for that.
Thank you.
Yeah. Any other closing comments or thoughts? Otherwise, will wrap us up here. Vinayak, thank you so much for your time and for the wonderful talk. We will be sure to stay in touch. And Danielle, thank you for introducing us to the speaker and for sponsoring the talk. And thank you everyone for joining. Have a
Thank you
great
so
rest of
much.
your day.
You too. Thank
thanks,
you.
Vinayak. Talk soon.
Sure.